First of all, can everyone hear me at this volume? Okay, so second, welcome back to day 2 of Practical AI. The lesson plan is going to be like, the lesson plan, we finished the homework survey and the announcements, and then we're going to talk about, we're going to go over some review of previous material, and then we're going to go into binary classification and then multi-class classification. Fancy words, but you'll understand once we're done. So actually, some announcements. Yeah, the homework survey you guys have all seen. Also, all the resources, like all the homework, all the YouTube videos, all the key concepts and stuff, they're all going to be on like our practical AI syllabus. So if I go over here, can you see? Oh wait, Nandita, how do you switch? How can I switch? Yeah, okay, so basically, this is the Practical AI syllabus. Here we have some, like, stuff. Here we have a course description. If I can... I'm sorry. Technical difficulties. Oh, there we go. Yeah, so basically, there's some general, like, talking about the course. And then you have a schedule and, like, each class, the lecture times, the office hours, the lecture slides, and then the YouTube link and homework. So like that's going to be your primary resource. If you guys ever get like lost in anything, don't know what the assignment is, just check the syllabus, and yeah. Okay, so cool. That's the syllabus. Go back to presenting. Wonderful. Alright, so now on to the review of last week's material. So as we learned last week, a machine learning model does two things. It predicts and it trains to make better predictions. Last week we learned about linear regression, which was predicting in a line pattern. Basically, I think the example that we took last week was given someone's grade, we wanted to predict the number of homework hours they had per week. And so, basically, linear regression would give you this line. Yeah. And so what the line represents is if we have someone over there, actually, I can use the pointer. If we have someone like that comes into a room, that walks into us, and we're trying to classify them to see how much homework hours they have per week, our prediction is that they have this amount of homework hours per week. Likewise, if someone comes in at this grade level, we'd predict that they have like this amount of homework hours per week. And again, if someone comes in at this grade level, we would predict that they would have this homework hour per week. So like the line kind of represents a set of predictions. How we, like given the grade, how do we predict their homework hours per week? Cool. So that was like linear regression. And that was how linear regression predicts how much homework hours you have per week. But how do you like pick the best line? How do you train your data or train your model? So we first introduced a concept of loss, or how bad your function is doing. So technical difficulties, please wait. So how do you...
It's good.
Oh, lag. There's a bit of lag, so yeah. Alright, so how you would... loss is basically a measure of how bad your function is doing. And so given, like, let's say, consider this person, right? Their current grade level would be somewhere around here. And then our prediction would be they have this amount of homework hours. However, in reality, they had this amount of homework hours. And so the red arrow kind of represents how many homework hours we missed. Likewise, the red arrow over here would represent how much homework hours we missed for that person. And so by adding all the red arrows up, you kind of get a sense of how bad your function is doing in general. And so, which function is doing worse, the left one or the right one? The right one or the left one? Does anyone want to give a chance? Sure. The right one, yes, that one is doing worse. And so, the reason why this is that, like, look at this person, for example. The model is not predicting, like, all of this homework. And so, it's doing pretty bad. And so, to get a good model, all we have to do is to find a model with like a very low loss. That means our model is doing very well. Okay, and another thing that we got into was that loss is based on your line's slope and its y-intercept. Given a slope and a y-intercept, you can uniquely find a line, and then using that you can uniquely find its loss. In other words, given any like w and any b, I can draw that corresponding line, and then I can calculate its loss. And so with that we introduced a new idea of a loss function. So a loss function basically took in a slope and a y-intercept, built the corresponding line, and then calculated and spit out the amount of loss that was corresponded to that line. So like the amount of loss of like this line would just be loss 1/3, 5. Okay, so does this make sense so far? Alright, so last week we had an activity where we basically, where I had some data points, and basically you guys gave me any random slope and any random y-intercept. And so we took a couple of slopes, a couple of y-intercepts, and we plotted the loss in each square. And so like for example, maybe we had w is equal to 1/2 and y-intercept is equal to -2, and we would calculate the loss, and then we could, and then we would just plot that. So I'm not going to actually go over the simulation here, but this is basically our result. For example, slope -1.5 and y-intercept -2 was like a really bad guess. It had a loss of like a ginormous 315. However, the best guess was a slope of 1.5 and a y-intercept of 0 that had a loss of 1.8. And so our whole question is, how can we find like, this best guess, this guess with the minimal amount of loss? Okay, but before we can get into that, we have to talk about another way of like visualizing this. So here we have loss plotted as height. And so, for example, this is a new data set, and maybe here a slope of 1 and a bias of like -3 over here is a really good guess because it has a low height and therefore a really low loss. But then slope of -2 and height of, or y-intercept of -2 as well, has a really high, or has a really tall loss and is a really bad guess. And so now we can kind of reframe our problem of like finding minimal loss, as in like how do we get to the lowest part of the graph? And so the way we did this was by gradient descent. Does anyone remember gradient descent and want to like give a guess? Sure. Yeah, so basically, given any hill, we would just like step downwards and at every instance, and then eventually get to a low point. And so if I go back, okay, yeah. So let's say we started at this square, 315, right? What would our next step? And let's say we knew like everything around it. What would our next step be? Yes? Yeah, 215, because that's like the lowest area that's, that we can see. And so we go and step to there. And then we would go to 137, and then like 72.6, and then 30.1, and then 68.3, and then 2.05 before finally reaching 1.80. And so, in other words, we just kind of take minor steps that make our guesses better and better and better. Yeah, and I guess we also had we had an animation that kind of demonstrates this idea. Basically, we start out with like a really bad guess that's like something like this, and of course it has this corresponding really high error. And then as we make tiny incremental adjustments, you can see that the slope our predicted line matches up the actual data more and more and more. And yeah, so that was gradient descent. And so that concludes most of the review. Finally, we review the first topic that we actually did introduce last class, which was regression versus classification. So let's say you're trying to predict housing prices. Do you guys think this is a regression problem or a classification problem? Okay, so I guess this is a regression problem because the outputs are a spectrum. A house can cost anywhere from $0 to like hundreds of millions of dollars. And we're not trying to classify them into like distinct categories. We're trying to find like a value in a range of values. Alright. What about given like a patient and their symptoms, trying to identify which disease they have? Would you guys think this is a classification problem or a regression problem? Yes. Indeed, this is a classification problem because there are very distinct categories. Like there's influenza, there's I don't know, chickenpox, and there's like measles. Yeah. All right. The outputs are certain categories. And finally, what about like given an image of a pet, trying to classify trying to figure out if it's a cat, a guinea pig, or a dog? What would this be? Indeed, classification, because there are like cat, guinea pig, and dog are distinct from each other. There's no such thing as like a dog guinea pig hybrid. Actually, at least I think there isn't. Okay, so yeah, now we're gonna move on to a topic called binary classification, and we're gonna explain in detail.
Is this how you do it? Okay. So binary classification is when you want to say something is either a yes or a no. So, for example, if you had this picture, then then maybe you could ask your algorithm to say, is it a cat or is it not a cat? Like there are only two options for your class. That's why it's called binary. So in order to approach this topic of binary classification, what we're going to do is we're going to assign probabilities to it being in a class. So for example, we could say the probability of being a cat here is 0.6. So if it's 0.6, would you say it's a picture of a cat or not a cat? Yeah, because it's greater than a half, right? This idea is called logistic regression, which is where your model predicts the probability of belonging to a class. It can be applied for binary classification as well as multiple classes. So this distinction is a little bit confusing. Logistic regression itself is a regression problem because it predicts the probability. And the probability is a numerical value like 0.6, 0.8 for any input. But if we take the probability and round it in the way that you guys just did a couple of minutes ago, and if we round it to the nearest class, then we get zeros and ones. So that's binary classification. So this is the way we're going to be approaching this problem today. So suppose that you have a picture of a cancer tumor and you want to classify it as malignant or benign. Like malignant means that it's cancerous, and benign means it's fine. So this is a 0-1 problem. Either it's harmful or it's not harmful. So suppose you have this graph. This is the data that you already know. So we're going to apply logistic regression to this problem. So let the y-axis be the probability that the tumor is malignant. And what happens if we try regular old linear regression? Yeah?
I guess, so right now, maybe mention y is probably 0 or 1. Okay, so basically a tumor can only be either malignant or benign. It can't be like anywhere in between.
Yeah, it can't be both.
In reality, the probability is only like 100% or 0%. But because we don't know everything, that's why we're trying to predict like a non-0 1.
It's a good distinction. That's also why in our in the initial graph, everything that is malignant is a 1, and everything that is not is a 0, because that's what we already know. Right. So, can anyone guess what happens if we try linear regression, just straightforward linear regression on this graph? Yeah? Mm-hmm. Mm-hmm. Okay, so there's actually a problem if we try just straightforward linear regression without doing anything to it on this graph. So here's a way we might do it, right? We might say that let 0.5 be our threshold. If the probability is greater than 0.5, then it's malignant. If it's less than or equal to, then it's benign. But if we just do normal linear regression, we could get values less than 0 or values greater than 1. And that doesn't make sense because we're doing probabilities. So there's a function called the sigmoid function, which graph is a curve. We're not going to go into the equation for now. So using the sigmoid function, we can squash this. Instead of using the regular function y equals mx plus b, we're going to use a function which squashes the output into the range 0 to 1. So up here, up here you can see how such a function works. So the intuition behind this function working is that you see how up here the distance gets very minimal, and that kind of makes sense around here, because if the probability of it being malignant is 0.95 versus being 0.97, that's not really going to have much of an effect on your class. But down here, in the middle, you notice that the line is steeper, which intuitively makes a bit of sense. So in order to get more of an idea for this function, we can go into certain, we can try plugging in certain values. So s of 0 would just be 1/2. So if your tumor has size 0, then it could be either. If your tumor has a size of 1, then there's a 3/4 chance. So the larger it gets, the more probable it is that it's malignant. If your tumor has a negative size, which kind of doesn't intuitively make sense. Yeah, you have something you want to say? If your tumor has negative size, which kind of doesn't intuitively make sense, then it has a really low probability of being harmful. Sorry. So to recap the differences between linear regression and logistic regression, linear regression is just a straight line. It's just y equals mx plus b, and you're trying to optimize the w and the b to get the minimum loss. But logistic regression is a curve. So you're trying to get a curve to classify as well as possible, and this curve never goes above 1 and it never goes below 0, because that's how probabilities work. Oliver had something to say? Okay, cool. Alright. Yeah, sure.
So, alright. So, now let's talk a little bit about how do you kind of visually represent your logistic regression function. So, the idea behind visual representation of logistic regression is it's all about the boundary. So the boundary is when probability it's malignant is 0.5. We have no clue if it's malignant or not. Likewise, if it's just a little bit if it's just a little bit smaller, then it would have a problem. Then we would classify it as not malignant. And if it was a tiny bit bigger, then we would classify it as malignant. And so by looking at these boundaries, we can kind of get a sense of what the model thinks, I guess. And yeah. So this graph kind of corresponds to this graph in a different way. So over here the graph means red means malignant and blue means benign, and the purple line corresponds with the boundary. So if we have a dot on the purple line, we wouldn't know what to do with it. However, if we had like a dot a little bit above the purple line, we would classify it as malignant, and if we had like a dot a little bit below the purple line, we'd classify it as benign. And so, yeah. So now we're gonna look at like and this might not be like too especially helpful in the one-dimensional version, but I think it's more helpful to see in the two-dimensional version. Yeah. So here we have a different problem. We're trying to predict if people have flip phones or not. So basically, the older you get, the more likely you're going to have a flip phone, and the less income you have, the more likely you're going to have a flip phone because you're trying to save money. And flip phones are cheaper than than smartphones. So here we see a boundary that distinguishes our guess of like flip phone users and not flip phone users. Over here we classify everything to the left of this boundary as a flip phone user, and we classify everything to the right of this boundary as a non-flip phone user. And that kind of like represents boundaries, I guess. Yeah. And so, so basically, if we had someone on the boundary, we wouldn't know what to do with them, because like the probability that they have a flip phone is exactly 1/2, and that's just a random guess. If they were to the right of the boundary, then the probability that they would have a flip phone would be maybe less than 1/2, and so they'd be classified as someone without a flip phone. And if they were a little bit to the left of the boundary, the probability that they would have a flip phone is more than 1/2, and so they'd be classified as a flip phone user. Yeah. And then the question becomes like, another way of intuitively thinking about logistic regression is just how do you find the best boundary? And the way we do that is by defining like another version of loss, basically how bad you are doing. So, do you think this is a good guess for the flip phone users? No, right? Because so if left is flip phone users and right is non-flip phone users, then we're classifying correctly all these circles and all of these pluses, but we're missing out on all of these circles and all of these pluses. We're wrong in that guess. And so we're not going to go into the exact mathematical formula, but basically using this idea, you can generate another sense of loss, and then you can again use gradient descent to minimize loss. And so we kind of have another animation here. You're trying to classify between x's and squares. I don't know what the actual difference is, but basically you start off with some random line, and then by minor tweaks, you get better and better and better. And like that's using gradient descent. Yeah. Okay. Alright, so now we know how to classify, let's see. Yeah, we know how to classify things into two categories, right? We know how to classify flip phone users or not flip phone users. In other words, yes or no to certain categories. In this case, flip phone users. Now, what about if you wanted to classify an image into, a cat, a guinea pig, and a dog? How would you do that? Well, the answer how would we do that is basically we'd build like kind of 3 models that would classify, So basically let's say you have an image, and we want to classify it to see if it's a cat, a dog, or a guinea pig. So we first classify to see if it's a dog. And if it has a probability of 0, and let's say it has a probability of 0.3, and then cat has a probability of 0.7, and guinea pig has a probability of 0.5. So what would we intuitively think that this is? A cat, yeah. And that's basically the general idea. Given any image, we classify the probabilities that it's a dog, a cat, or a guinea pig, and then we just take the one that's the biggest. Yeah. Alright, so now we're going to move on to implementation.
Like to put what Oliver just said into more general terms, if we have any multi-class classification problem, then we can break it up into smaller binary classification problems. See which one we used earlier. Like for each class, we like probability yes or no. Okay, so we're going to send out...
Wait.
Yeah?
Should we actually see if we want to re-explain anything?
So, are there any questions?
Yeah, like, does anyone not understand anything? Most common.
What would you do with the Oh, so for everyone, the question was for real life, what would you do with the data that's in the middle, like this? Okay.
Yeah, like,
I so that's a question that would depend on the data set. Like, to think like how much do I want like a false like so suppose you're doing that cancer, but it's not. Then you can't give them a false negative. You can't say no, you don't have cancer when actually they do, right? Because that would be good. So then maybe you would be like more like inclined to say no, it's not cancer. Like sorry, to say yes, it is cancer if it's on that boundary line. But if you're doing something else that's a bit more trivial, then like maybe you would.
so basically, like, yeah, failing to detect cancer is much more harmful than actually giving a false alarm. And so basically, you tend to like err on the safe side and try to say that, oh, if it's unsure, then yeah, just say that you do. Yeah. Yeah, so, yes. No. Yeah, so like, for example, maybe my burrito cat looks really like a cat, a guinea pig, and a dog. Yeah, then we wouldn't. So yeah, they don't have to add up, I guess. Yeah. There are ways of making them actually add up by kind of taking like a weighted average of the probabilities. And that might make more sense if you're like actually looking for the probabilities that it's a cat, dog, or a guinea pig. Yeah.
Any other questions?
Were there any like questions on logistic regression and like this?
This stuff is complicated.
Like, don't feel that you have to get this in the first try. The reason why we have a class like this is because like this way you guys can ask questions. So I guess if you guys have any questions, you can say them now, or like we're gonna be going around at implementation time.
Yeah.
And you guys can ask us then.
We're gonna taking a break and then implementation time. So
yeah.
Anytime.
So.
All right, cool. So we're gonna take a short break now, and resume around 4:55. 4:55.
Snacks, I guess. You didn't come last time, right? Yeah, so this might have been overwhelming for you a little bit, so if you want like any extra like questions, or if you want to ask any extra questions, that's also fun. Yeah. I'm gonna go around and get everyone's name again. I totally forgot them. Alright, what's your name again? Michelle, right? What's your name again? Katrina. Okay. Michelle, Katrina. What's your name again? Ashika? Anshika. Okay. We're just taking a break for like 15 minutes or so. Hawaii.
There was bad weather, so we diverted our flight to Honolulu. So we got home a lot later than we got home. So I went to bed at 1 yesterday. It was bad. So I expected to go to bed at 1.
What's your name again?
Sindini.
Sindini?
Yeah.
Anshika Sindini?
Yeah.